This lecture is on the derivative, the inverse of a function. Let's begin by reviewing what a function is. A function is a relation between two sets. And we're going to call these sets domain. We're going to denote that by domain. We're going to denote that by D, and range. We're going to denote that by R, such that for every x in, so this notation you might be familiar with. This means x is an element or is in the domain. For every x in the domain, there is only one y in the range. X's are the members of the set domain, and y's, we just call them y's, you can call them whatever you want, are the members of this set range. A set is a group of things. And if you think about it, this definition should make logical sense. And I'll tell you why in a second. Let's say we have a set, and typically we use a Venn diagram for a set. I'm going to use a number line or a part of a number line, which is an interval. We're going to call this the domain of F. We're just going to use the letter D, and X lives here, let's just say. And there is another set. Again, I could use a Venn diagram. Let's just say this is some closed or open interval. This set is called the range, and Y lives here. So the function is like a processing machine. It takes X in and it gives you Y. Imagine Alexa or Siri. You ask Siri a question. What time is it? Well, Siri is just going to give you one answer. And imagine that Siri is programmed, or you have this machine of your own, like Siri or some sort of AI, that is programmed to answer a certain set of questions. It can't answer all the questions in the world, so it is limited to answer a bunch of questions. If it could answer all the questions, it would be as if the set is from negative infinity to infinity. It can give you a bunch of answers. If you ask your machine, your AI, a question, your AI is going to give you only one answer. So, for example, you can ask it what time of the day it is. It's going to tell you it's 12:55 p.m. It can't tell you it is 12:55 and it is also 1 p.m. That's just logically nonsense. So that's what a function is. Let me give you a quick example of a function. Let's say we have a set of all reals. That is the domain, and the range is the set of all non-negative numbers. So it's from 0 to infinity. Let's say our function is x squared. And we take a number in the domain such as 2. And what the function does is that it takes 2 in, it squares it, and it gives you one answer only. And that answer is 4. So here we have an example of a function f of x equal to x squared. We have a special type of a function, which is called a one-to-one function. Let me define that over here. One-to-one function is, of course, a function. By definition, it says one-to-one function, so it's a function such that for every y in the range, there is only one x, which we also call the input in the domain. Okay, keep in mind, y is called the output and x is the input of the function. Okay, so for a one-to-one function, for every output, we want only one input. Let me show you an example of a function that's not one-to-one. We're going to refer back to the previous example. I'm just going to copy and paste to save some time. We took 2, and which was a number in the domain, we got an output of 4. Now let's say we take another element in the domain. Say we take -2, and the function takes -2 in, squares it, and guess what? It gives you as well. So what's happening here is that for the output of 4 in the range, there are 2 different inputs. Those inputs are x equal to -2 and x equal to 2 in the domain. And this clearly is violating the notion of a one-to-one function. Let's look at a function that is one-to-one. And let's once again take for the domain the set of all reals. For the range, I'm going to take the set of all reals as well. And let's say that our function here is x cubed. All right. And let's say we take a number such as -1 in the domain of the function. The function x cubed takes -1 in, and it gives you -1 in the range. Okay? You are not going to be able to find another number in the domain that will give you an output of -1 in the range. There's no way that I can find another number in the green set that I cube and I get -1 as the output. This is an example of a one-to-one function. F of x equal to x cubed is 1-to-1. And here f of x equal to x squared is not 1-to-1. And I'm sure you're familiar with this notion from algebra. We're going to see why one-to-one functions are important. for instance, the graph of y equal to x squared. Here is f of x equal to x squared. Let's pick a few points. 0, square of 0, 0. As we saw, -1. The square of that is 1. And for 1 in the domain, the output 1 squared is also 1, creating our famous parabola. And we know that for a graph like this, the horizontal line crosses the graph at more than one point. If it does, then it means that for every y, there are multiple inputs. Okay? If a horizontal line passes the graph more than once, again, that means that for a y in the range, there are two distinct x's in the domain. All right. And the other graph was the graph of y equal to, or f of x equal to x cubed, or graphing f of x equal to x cubed. This is the S-shaped graph. And again, I'm sure a lot of you are familiar with this graph. Let's plug in 0. 0 cubed is 0. 1 cubed is 1. -1. The cube of -1 is -1. You could pick more points. For instance, you can pick 2. 2 cubed is 8, or -2 will give you -8, creating the S-shaped graph. If you have access to the graph of the function and any horizontal line crosses the graph only once, then we know it is a one-to-one function. Again, horizontal line, I'm going to call it HL, crosses only once. And here, the horizontal line, or a horizontal line, crosses multiple times. So again, if this happens, function is not one-to-one. And if crossing once happens, the function is in fact one-to-one. We not always have access to the graph of a function. Imagine a function such as square root of x plus the sine of cube root of x. Graphing that is time consuming. So what do we do? How do we know if the function is in fact one-to-one? Notice something stands out about the graph of a one-to-one function versus the graph of a non-one-to-one function. A non-one-to-one function is not monotonic, meaning that it doesn't always increase or always decrease on its domain. As you see, this graph is decreasing sometimes, and sometimes it's increasing, whereas the graph of a one-to-one function is monotonic. As you see, this graph is always increasing. You can have a decreasing graph like this, and as you see, this graph is one-to-one because if I draw a horizontal line, it crosses only once. So how do we know if a graph is one-to-one? We can check to see if the graph is always increasing or always decreasing on its domain. And for that, we use the first derivative. That's a rule that you can use if f of x only increases or only decreases on its domain, then it is 1 to 1. Of course, on its domain. And we can check for increasing, decreasing by looking at the first derivative. If the first derivative changes sign, then we know the graph is sometimes increasing, sometimes decreasing. And if there is no sign change, then the graph is monotonic. For instance, let's look at f of x equal to x plus sine of x on negative infinity to infinity. F prime of x is equal to 1 plus the derivative of sine x is cosine of x. What is special about 1 plus cosine x? Well, we know that cosine and sine are bounded functions. They're always between -1 and 1. Cosine of x goes from -1 to 1. The amplitude of cosine is 1. Our derivative here is 1 plus cosine of x. So I am going to take this inequality and add 1 to every side of the inequality. So here we have -1 plus 1. Okay. The expression in the middle, cosine of x, add 1 to that. So we have cosine of x plus 1. Add 1 to the right side of the inequality as well. The middle is the derivative here. We have basically 1 plus cosine of x being between 0 and 2, or I should say f prime goes from 0 to 2. What does this mean? This means that the derivative will never change sign. The smallest the slope of the tangent line can be is 0, meaning that sometimes the graph has horizontal tangency, and the highest that the slope can be is 2. The slope is never negative. So our graph is always increasing on negative infinity to infinity. And let me actually demonstrate this. Here I have the red graph is the graph of x plus sine of x. The blue line is the tangent line, and I am going to vary x's on the red graph. Therefore, you're going to see different tangent lines. Look at that. If I put the point at that location, point A, you could see that slope is 0. And as I move the point to the right, slope is increasing. Okay, so right about here, slope is 1, and then slope keeps getting higher. Right about here, slope seems to be 2. And if I keep going, slope is going to decrease back to 0. And the same thing is going to repeat. So slope is going to start from 0, and the highest it can be is 2, and then back to 0. The slope itself is periodic. You can actually see the slope. If you look at M, you can see that M is varying between 0 and 2. And then decreasing to 0. And then increasing back to 2. And the same thing is just going to keep repeating. And as you saw, the graph was always increasing on its domain. Our function x plus sine of x is 1 to 1. The 3 dots mean therefore is 1 to 1. Well, why is the definition of 1 to 1 important? If a function is 1 to 1, then its inverse exists. What is the inverse of a function? The inverse of a function is a function that takes an element of the range in, and it gives you the corresponding element in the domain. So let's say we have, again, the green set. This is the domain of the function. And we have the red set. This is the range of the function. And let's just assume that x lives in the domain of the function. Let me call that, instead of x, let's just call it a. And say b is an element of the range. And what f does is that f takes a in, and it gives you b in the range. But f inverse does the reverse. So if you want to retrieve a knowing b, we are going to take b and we're going to plug it into the inverse function, which is denoted as f with a superscript -1x. Sometimes we want to retrieve the input if we know the output. And imagine if the function is not 1 to 1, meaning that we would have, let's say, 2 different inputs, let's say A1 and A2, with the output of B, then going back, the inverse would give you 2 different outputs. And we don't want that. We don't want f inverse of x to have two different outputs, else it would not be a function. That's why one-to-one functions are important. Notice that b comes from the range of f. It is actually also the input of f inverse of x. So the red set is also called the domain of f inverse, and A is the output of f inverse, and outputs are in the range of the function. So the green set is also the range of f inverse. As you might remember, the domain of f is the same as the range of f inverse, and the domain of f inverse is the same as the range of f. The relation between a function and its inverse, as you can see from this picture, is that if f of a outputs b, then a is f inverse of b. Basically, again, f and f inverse, they switch their input and their outputs. As you see, a is the input of f, but at the same time, a is the output of f inverse. Likewise, b is the output of f, but at the same time, b is the input of f inverse. You might have learned about the derivative of a function, but what about the derivative of the inverse of a function? The derivative of f inverse of x at a point is what we want. If you're given a function and you want to find the derivative of its inverse at a point, you have one option, which is not the best option, and that option is to use algebra to find f inverse of x, and then take the derivative of f inverse of x, and then plug the point. But in almost 100% of cases, algebra is not going to work. For instance, for the earlier example, finding the inverse of this function is not going to be too easy to do. So there must be an alternative. And to derive the derivative of f inverse, I want you to recall what's called the inverse composition identities, which tell you that if you take a function and compose it with its inverse at x, you get x back. And likewise, if you put f inside the f inverse, you should get x back. This kind of makes sense because if I have the domain and range, and let's just say we start with x, I'm not going to go back and forth with the colors. f is going to act on x and give you, we can call that point in the red set or in the range y, or we can just leave it as f of x. Going back, assuming the function is 1-to-1, we are going to use the inverse function. And what we are going to plug into the inverse function is f of x. So imagine this f of x is our b from the last example. And you're putting that into f inverse. And that, of course, outputs x. It gives you x back. Okay, so this is what we need in order to find the derivative of the inverse function at a point. So let's go with one of these composition identities. Let's go with f of f inverse of x must equal to x. An identity is an equation that's always true. So again, if the function is assured to be 1-to-1, this composition must be true. Okay, it's an equation that's always true. And since we have an equation, we can take the derivative of the left and the right hand of the equation. I'm going to apply the derivative operator on the left. And likewise, take the derivative of the right. On the right, we have dx, which is just 1. But on the left-hand side, since we have a composition, we need to use the chain rule. And the chain rule says that if you have an inner and an outer function, you start by differentiating the outer function. So we take the derivative of f at f inverse of x. We're going to multiply that by the derivative of the inside function. That's going to be a little bit hard to write down. So that's f inverse of x derivative. Okay, it's going to be a little bit weird if I put the prime right there. This again indicates the derivative of f inverse. What we want is the derivative of the inverse function, which is sitting right there. All you gotta do is just divide this equation by this factor. If you have an inverse function, its derivative is 1 divided by the derivative of the original function at the inverse. So to make things a little easier to look at, I am going to let, in this case, g of x be f inverse of x. And that's because I personally dislike that notation. The -1 looks like an exponent to many. They do not interpret that correctly sometimes. And what we want here is the derivative of g, right? F inverse is G. So the derivative of G at a point, let's say that point is A. So here again, G prime stands for F inverse prime. And we're evaluating that at some point. This is equal to 1 divided by the derivative of f at the inverse function at a. So this is the formula for finding the derivative of the inverse of a function at a point. Let me start with an example that we can do directly and indirectly. I intend to show you that this formula is believable, and that's by confirming it through an example that we can do. Let's take a function easy enough whose inverse can be found. So for instance, let's say we have f of x equal to x cubed. X cubed is 1 to 1, therefore it has an inverse. We can find its inverse. We're going to let g of x be f inverse of x. So I'm doing this again for convenience to avoid writing that notation, the -1. The question here is to find g prime of 8. This is the derivative of the inverse of x cubed at 8. Let's do this directly by first finding the inverse function. All right, so here we have y equal to x cubed. If you're finding the inverse of it, switch x and y, input output switch. X is equal to y cubed. Solve this equation for y. We're going to get x to the power of 1/3 equal to y. Therefore, here g of x is x to the power of 1/3. And then we can take the derivative of the inverse function. G prime of x is, using the power rule, bring down 1/3, subtract 1 from the power. You get 1/3 minus 1, that's -2/3. You can write the inverse as 1 over 3 times x to the power of 2/3. And then, since we are asked for g prime of 8, we can plug 8 in. That will give us 1 over 3 times 8 to the power of 2/3. We can begin by taking the cube root of 8. What we have here is basically the cube root of 8 squared. And that is equal to 1 over 3 times cube root of 8 is 2. Square that, you get 4. So in the denominator, we have 12. 1 over 12 is the derivative of the inverse at 8. So this is given that you can, in fact, find the inverse function. Let's try to use the formula that we have derived earlier. So the formula said that g prime of 8, a, here is 8, is 1 over f prime of g of 8. So here we need two things. We need the derivative of f. We know that here f is x cubed, whose derivative is 3x squared. I also need g of 8. But I don't know what g of 8 is, so I can call that, let's say, a. Since we know that g is the inverse of f, 8, that is the input of g, is going to now be the output of f. So 8 is equal to f, and a, who is the output of the inverse, is the input of the actual function. Again, this is the relation between a function and its inverse. We know what f is. F is x cubed at a. That be a. You can keep that as x if you want and get 8 equals to f of x. But to find a, just take the cube root. The cube root of 8 is 2. So what we just found is g of 8. We call g of 8 a, and a is 2. All right. So now, according to this formula, g prime of 8, this is equal to 1 over. So we have access to the derivative of f. The derivative of f is 3x squared. This is going to be f prime of g of 8, which we just found. G of 8 is 2. You are plugging 2 into the derivative of f. As I said, we have access to it. So we get 1 over f prime is 3x squared. Replace x with 2. And that gives you, once again, 3 times 4, 12 in the denominator, 1 over 12. We've obtained the same result as before. But again, the deal with the direct method is that in most cases, we are unable to solve for the inverse function algebraically. Once again, as I said, our earlier example, f of x equal to x plus sine x, is a function whose inverse is, I'm not even sure if we could find the inverse of that. You can't. Imagine you set x equal to y plus sine of y. How do you solve for y? In which you would get the inverse. We can't. So we have to rely on the formula for the derivative of the inverse. So let me finish by actually using that example to find the derivative at some points. So here again, f of x is x plus sine of x. And again, to make things simple, we're going to let g of x be the inverse function. The question here is to find the derivative of the inverse at, let's say, 0. So let's write down the formula. We know that f is 1 to 1. We've proven that it in fact has an inverse. Therefore, g or f inverse of x exists. So again, by the formula, g prime of 0 is equal to 1 over f prime of g of 0. So f prime is something we can find using whatever derivative rule. F prime of x, which we've already found, is again 1 plus cosine of x. So keep that in mind. We need to also find g of 0. So what you're going to do as before is to let g of 0 equal to a. Therefore, 0 becomes f of a. So once again, 0, which is the input of the inverse, is now the output of the function. And a, which is the output of the inverse, is the input of f. So this forms an equation that you can use to solve for a. We get 0 equal to f is x plus sine of x. Replace x with a, you get a plus sine of a. So this is an equation that we need to solve. Please don't try to use algebra or trigonometry to solve this equation. You just have to guess. This is called solving by inspection. What do I plug in for a to get 0? And hopefully the answer is obvious. The a must be 0 because we know that sine of 0 is 0. And if you add that to 0, you get 0. So by inspection, a has to equal to 0 since 0 plus sine is 0. So we just found a, which is the same as g of 0. And we're going to plug that in to our formula, which is 1 over f prime of g of 0 is 0. It's just a coincidence that the output and the input of g in this case are both 0. They don't have to be. Again, we have the derivative of f. The derivative of f is 1 plus cosine of x. Plug 0 for x. So you're going to get 1 plus cosine of 0. And that's equal to 1 over 1 plus cosine of 0 is 1. But we end up with 1/2. Okay. So what does that mean? Here we have a function that has an inverse, but we don't know what the inverse function is. If we knew what the inverse function was, we could have taken the derivative of it and we could have plugged in 0. But whatever the inverse function is, the derivative of the inverse function at 0 is equal to 1/2, which you can say that the slope of the tangent line to the graph of the inverse at 0 is 1/2.